Okay, so today we're going to be talking about volume. Now, before I go into this, let's just redefine area, which is what we did in the last video. So we looked at this idea, well, the last series of videos, I should say, but we looked at area as the kind of space taken up, which is enclosed within a shape. So everywhere in between our four corners of our square, the area makes up the whole portion within this. So I'm going to say, for example, that the area of this, well, I'm going to just give us some measurements here. So say this is a 4 centimeter by, let's make this a rectangle. Oh, can I do that? I can't. That's okay. Let's work with a square for now. So this is a 4 centimeter by 4 centimeter square. So looking at our area, this will just be 4 times 4, which we get an area of 16 centimeters squared. Now, a lot of these 2D shapes is what we call, well, these are what we call plane figures. They exist on just a 2D plane. So if I drew, say, a square or a triangle or any shape on a flat kind of piece of paper or on the ground or something, they don't contain a third dimension. They have no sense of, sorry, thought I had to sneeze for a minute. They have no sort of depth associated to them. They are just flat on our page and they're just there. They exist on a 2D plane. So a plane ranging going from this direction and this direction. But in the real world, a lot of the things we look at are 3D. You look at a book, for example. It has its front cover. Let me actually just draw one really quickly. Say we're looking at a book. It's got the front cover, whatever, and it also has a certain depth. And this is taken up by various different pages here. Now, my drawing's shocking. This looks more like a loaf of bread or something. But you'll see everywhere around us, even a loaf of bread, right? It's got 3 dimensions. It's got its kind of first piece of bread, and then it's got all the other bits that go out, that make up this third dimension. Now, going back to our square idea, is when we, might just rub this out, but just to give you some real world impressions of this. But in the real world, for example, things aren't in 2D, they have a third dimension. So there is an associated depth in a lot of our real world objects. And this is where you get a 3D shape. Now, in a similar way to what we did in area, but not really, we're gonna look at the depth of certain shapes and what this depth or breadth tells us about volume. Now, one important thing to note, I'm going to make this a cube, for example. So it's going to have all 3 dimensions equal. And this is a cube is a type of prism. And a lot of the areas will be, sorry, not areas, volumes we'll be working with are going to be at this stage of prisms. So this one here, just as a little kind of thought experiment, for example, have a look at our first square. Could we say that this square essentially goes all the way through our shape? It it kind of reoccurs, say here, or we can also locate this shape here, and I'm gonna just draw this little dotted line for you to see. It also reoccurs here. It goes essentially all the way through, doesn't it? So I have this here. And this is where area and volume are related. Because in all prisms, we have what is called a cross-sectional area. So an area that's maintained all the way through our shape. Hopefully that's relatively, hopefully you're able to see that within our shape here. But we have our second kind of little square. So all the way through here, these are all different squares. We maintain this. This is a cross-sectional area that goes through. So these two are quite related. I've made here our 2D kind of plane shape, which deals with, for example, areas deal with a bird's eye view of things, for example. So if you're measuring land, I'm measuring one dimension by another dimension. I'm looking down at it. Whereas 3D, in our volume, when we deal with volume, we have three different dimensions we're working with. Now, when we have our third dimension, well, we can say, for example, let's say each of these little slices I've made, and I'm going to draw this in a different color. Let's say each of these are 1 centimeter. Oh, no. 1 minute, sorry. And we have 1 centimeter. All of these little portions, I've broken this cube into like smaller bits, right? So I have this one here, and I have 4 lots of these. Now, if I were to take the volume of this first one, which has my 1 centimeter, well, I have 1 lot of this area. So that's the effect of multiplying our first area just by 1, which just gives me 16 again. Now, when we take volume, we see, I guess, when we've drawn each of these as 1 centimeter, we're almost taking 4 lots of this cross-sectional area. As in 4 of these are embedded within our cube. And this is why I drew sort of all these little ones here. But we can say, well, there are 4 of our cross-sectional areas based on the unit of centimeters within this. So taking 4 centimeters lots of our 16 centimeters square, 16 centimeters squared square, I should say, that is the effect of going, well, our volume is the area of our cross section. So 4 by 4. So it's going 4 centimeters by 4 centimeters. And then taking 4 lots of that in our depth, in our third dimension. So when we find certain volumes of, this is the easiest case, this is just a cube, all of equal, all sides and dimensions of equal length, we are multiplying all of these together. So here we get 4 times 4, we get 16 centimeters, and multiplying our cross-sectional area of 16 centimeters squared by our depth, we get 64 centimeters. And once again, from the previous video, when we multiply these, we also take into account the units. So we have 64 centimeters cubed. And the way we work with volumes of prisms is we take whatever our area of our front face. So say I were to draw a triangular prism. Let's do another example. Oh, that's not. There we go. Say we have a triangular prism. So triangular prism, it has these straight edges, again, similar to our cube. And we also have our having a lot of technical difficulties today. Sorry about that. We have here and it's not very well drawn, but you can see that once again our cross section goes all the way through. Our front face is kind of always present all the way through this shape. All the way to the back here. Now, this will be some good revision for calculating areas of triangles. So if I say had 2 centimeters here and we had a height, a perpendicular height, that's important to note, of 4 centimeters. And a depth of, this isn't to scale, but let's say 5 centimeters here. So finding the area of a triangle, we said, so I'm actually going to write here, I'm going to write CS for cross-sectional area. That cross-sectional area is from what we had with the area of our triangle, that's half multiplied by the base length multiplied by the height. And all our volume is going to do is we're just going to multiply that by our depth of 5 centimeters here. So our total volume, I'll do that in another color as well. Our volume equals our cross-sectional area multiplied by our, multiplied by our depth, D. And we've done the same thing here. We had our cross-sectional area, our front face, multiplied by, in this case, a depth of 4 centimeters. Now, what's our cross-sectional area? Well, we have half multiplied by our base of 2, multiplied by our perpendicular height of 4, multiplied by 5 here. So, first finding our cross-sectional area, 2 times 4 multiplied by a half, we get 8 multiplied by half, which is 4. 4 centimeters squared multiplied by 5 centimeters as our depth. And once again, we eventually get 20 centimeters cubed. And our different volumes depend on, at least for prisms, they depend on our cross-sectional area that we establish. So this could be a trapezium, a parallelogram, a triangle, a square, a rectangle. But we, in order to find our volume, multiply, well, in this case, whatever gives us our initial cross-sectional area, and we multiply that by the depth. So you can probably tell that I'm not going to give this one overarching formula Because for prisms, it depends on whatever our front face is, whatever our cross-sectional area is going to be. So the formula is going to be different for a triangular prism versus a rectangular prism, because that front face is different. So I've just written it here as cross-sectional area multiplied by the depth. And I'll explicitly write that there. I hope that all makes sense. We'll stick with prisms just for the time being. But once you know the areas in my previous videos, you can see parallelograms, trapeziums, different types of front faces. We can then just, once we find those areas, multiply by depth to get our volume of our solids, the volumes of our prisms. I'll see you next time.